Hi, I'm Bill Reese, and in this video, we're going to take a look at the spreadsheet duration and modified duration examples. And also, it has a convexity example in it as well. And this is based upon the class notes that are titled duration, modified duration, and convexity. So the numbers that we go over in the class notes are are calculated in Excel, that spreadsheet. So I'm going to pull up that spreadsheet and we're going to be showing you the calculations in the spreadsheet here. So you can follow along how to calculate duration, modified duration, and convexity in a spreadsheet and see what they are measuring and how they work. So let's pull up that spreadsheet. Um, let's see, duration and modified duration examples. Here we are. Okay, so you should be looking at the spreadsheet with me. This is bond number one from the class notes, which has a face value of $100, a coupon rate of 8%, matures in 2 years. Its bond equivalent yield or yield to maturity, either one, is 10%. Here's how the price is calculated using the present value function, present value of the cash flows, 96.45, and we show you that in the class notes. We've got this set up so that the settlement is whatever day you open up the spreadsheet, and the maturity is 2 years later because there's my maturity is in 2 years. Now, the duration is calculated really easily with the duration function. We've got a nice duration function in Excel, and you see what the inputs we need to get that is we need the coupon rate, we need the yield on the bond, we need the settlement date, and we need the maturity date. So if we've got those things and the frequency, how frequently are the coupon payments? And you can put basis in if you want to as well for how days are counted. I think I left it blank in this case. But at any rate, there is the duration of the bond. And then the modified duration, we've also got a modified duration function in Excel, very helpful. And it actually has the exact same arguments as the duration function. So for that particular bond, very simple bond that matures in 2 years, what we're going to do here is we're going to show here is the price now and what is the price going to be if there is a change in interest rates of 1%. And we can change that number around. We can make it 2%, 3%, negative 2%, whatever we want it to do. So the face value is still going to be 100. The coupon rate is still going to be 8%. The maturity is still going to be 2 years. But if interest rates go up by 1%, the new yield on the bond will be 10% plus 1% is 11%. And so if the yield is 11%, then the price of the bond, interest rates go up, the price of the bond goes down from 96.45 to 94.74. So how much of a drop was that price change? How much did it go down by? Well, it went down by 1.7747%. You can go on further decimals, as you can see there, if you want to. So it went down by 1.77%. So the question is modified duration, which is a first order approximation of this price change. What did modified duration predict it would go down by? Now, actually, a 1% change in interest rates is huge. Okay. We normally have interest rate changes that are just a few basis points. So, modified duration says that for every percentage change, which is what we got here, a 1% change in interest rates, there will be a 1.795457% change in the price of the bond. So we take this 1% and multiply it by the modified duration. And modified duration is predicted interest rates go up by 1%, the price of the bond will go down by this. So modified duration predicted a bigger price change than there actually was. And how much was it off by? By that amount. Now, is this a good approximation or a bad approximation of that? This is the approximation of that. Well, it depends upon how close you want it to be. Now, I would say for just a few basis points, it's pretty darn good. So if we're talking about, let's say, 5 basis points instead, okay, 0.0 5% being there. Now we're talking about, you can see that the predicted change was 0.08977 and it was 0.08972. We're getting, talking about really small differences here in terms of how much it is off by. So modified duration does a very good job for relatively small changes in interest rates there. Okay, so what we want to do now is take a look at bond number two, and you can play around with this, changing around different numbers. Now, if there's a big number change in here, say, let's say, for example, like 3%, now the predicted change was I'm sorry, the predicted change was for the price to drop by 5.38%, and it dropped by 5.20%. Now, that's a big difference there. Okay, a significant difference. So modified duration is going to be good approximation for small changes, not as good for larger changes. Bond number two is going to work very similar to that. Okay, here's the face value of the bond. Here's the coupon rate, 8.4%. This bond matures in 6 years. It has a yield of 9%. Here, the price is being calculated based upon that information. The settlement is whatever day you open up the spreadsheet. The maturity is going to be 6 years later. Here is its duration. I'm using the duration function. Here's its modified duration, using the modified duration function. And of course, if interest rates go up by 2%, then the yield goes up from 9% to 11%. The price drops from 97.26 to 88.8. That is an 8.7% drop in the price. And modified duration had predicted a 9.2%. How did modified duration do that? 2 times the modified duration is 9.214. So this is how much modified duration was off by in that particular bond. And again, you can play around with this to see the different changes there. So this is showing you here, okay, how modified duration is projecting the change in the price of bonds. And again, if we have relatively small ones, let's make this 0.02%. And we can do negatives as well, of course, in there. That the price of the bond went down by 0.092%. The predicted change was 0.092%, 0.0921. So there's just a little bit difference in terms of what modified duration projected versus what actually happened. And so for small changes, modified duration does a pretty good job with things. Well, if we want to be more specific because we are concerned about large changes or we just want to be more exact, we add convexity to the mix. So we're going to calculate the convexity for bond number one. Unfortunately, there is no function in Excel for convexity, so we actually have to go out and calculate it. So that's what we're doing now. This is a fairly easy bond because it only has 2 years until maturity. So what we've got over here is time period 1, that's 6 months from now. Time period 2 is 1 year from now. Time period 3, that is 18 months from now, and time period 4, that is 2 years from now when the bond matures. Here are the cash flows in those time periods, right? So 8% is the coupon rate on the bond. So semi-annual coupon payments. So it's going to be 4, 4, 4, and 104. These are the discount factors. Discount factors are simply going to be 1 over R raised to the T, okay? R is the semi-annual yield. So there's my yield to maturity divided by 2 raised to the T. That's to the first power. Here is going to be 1 over R raised to the T, where T is the second power, okay? And so forth. So these are the discount factors. What the discount factor allows you to do is to multiply the cash flow times the discount factor, and it gives you the present value of the cash flow. So these are the present value. This is the present value of this cash flow to be received 6 months from now. This is the present value of this cash flow to be received 1 year from now. This is the present value of this cash flow to be received 18 months from now. This is the present value of this cash flow to be received 2 years from now. Now, guess what? If you add up the present value of the cash flows, what should you get? you should get the price of a bond, right? The price of a bond is the present value of the cash flows. And guess what? The price of the bond here is 96.45. Guess what we had over there? 96.45. And if we took this out more decimal places, you'd see the exact same thing, okay, as we've got over there. So good news, okay, that's exactly what we would expect to see there. So now what we're going to do to find the convexity measure for the bond is we're going to do time period 1. Okay, we're going to do the present value of the cash flows, okay, right there, times time period 1 times time period t plus 1. So we can see what we're doing there. It's the present value of the cash flow in time 1 multiplied by the number 1 multiplied by the number 2. Okay, that gives us this. Here we have the present value of the cash flow in time 2 multiplied by time 2 multiplied by time 3. And here we've got the same thing. Here it's going to be the present value of the cash flow in time 3 multiplied by the number 3 multiplied by the number 4. Here is the present value of the cash flow in time 4 multiplied by the number 4 multiplied by the number 5. So we take that and we sum them up, right? So we're adding those numbers together. And that then we take and we're going to divide it by 1 plus r, okay, squared, where r is going to be the semi-annual yield, right? So B5 is 10% semi-annually. It's 10% divided by 2, and we're squaring that. Okay? So that's going to give us this number right here. Now, that is my convexity measure in semi-annual periods because we were counting semi-annual periods here, but we need to get it in years. So we need to divide by 4. A lot of times students say, why do we divide by 4 rather than dividing by 2? Well, the reason why is back in here, we were multiplying by one time period and another time period, which in other words, so we've got to account that we're multiplying by 2 time periods, and that's why we have to divide by not by 2, but by 2 squared to get that. So we divide 2 squared is 4. So we get that. So there's our convexity measure, 4.189, blah, blah, blah. So my formula for my predicted change when I include the convexity measure is right here, okay? That's going to be my using my modified duration. So this is just right here in the brackets is just using modified duration only. But when I include the convexity measure, I'm adding 1/2 multiplied by my convexity measure multiplied by my percentage change squared. And that is going to give me now my predicted change. Now take a look at this. Okay, when there's this 3% change here, okay, the actual change was 5.2%. What modified duration predicted was 5.38%, okay, closer to 5.39%, which is off by a little ways. What is it when we add the convexity measure in there? 5.198, okay, as opposed to 5.2. Very, very close. If we have, let's say, a 1% change here, then we've got, this is still pretty close to this, but you can see there's a difference between 1.774 and 1.795, but this is also 1.774, okay, but it's 1.774.5 compared to 1.7747. So no matter what the change is, the predicted change when you add convexity to our modified duration is going to make it a closer prediction. Now, we're not going to use convexity a lot, but I want you to understand what it is and how it's calculated. It would be a second order approximation because we are, think of it as modified duration as being the first derivative and convexity being the second derivative. So we are adding the second derivative to the first derivative in a Taylor series expansion to give us a better approximation of the function is what we're doing. If you didn't understand all that, that's okay. Just understand that it is a better prediction, but we're going to most of the time say that modified duration is good enough, but I want you to know how to calculate the convexity measure for a bond, and as well as understanding why more convexity in a bond is a good thing. So hopefully the spreadsheet helps you to be able to see how we got some of the numbers that are there in the class notes.